This clip's about equilibrium. Equilibrium is involved with a reversible reaction. A reversible reaction takes place, and at equilibrium, or more specifically dynamic equilibrium, where dynamic means to move, the rates of the forward and backward reactions are the same, and the concentrations of the reactants and products are remaining constant. They're not necessarily the same concentrations. So in the example of A goes to B, where A are the red dots and blue is B. If a blue dot changes into a red dot, a red must change into a blue. So if we have, say, this red one here, that one reacts to make a blue dot, another blue dot somewhere else must react to make a new red dot as well. So that's dynamic equilibrium. So at that point the concentrations are remaining constant. Now another important idea to understand is called Le Chatelier's principle. Now in a reversible reaction, if dynamic equilibrium has been reached and then we try to change the situation, the equilibrium will move to reduce the disturbance in the direction of the reversible reaction to reduce the disturbance. So for example, if we add more A into this system here, then the equilibrium will try to reduce the amount of A that's been added in, so more B would be made. That's called Le Chatelier's principle. So looking at the other example I've got here, A plus B goes to C and D, so a new situation to the one already described in this picture here. Now if we add more A to this situation, then the equilibrium will try to reduce the disturbance by shifting to the right hand side. So add more A, more C and D will be made, and the amount of A will reduce. If we remove A, so a new example number 2, remove A, then the equilibrium will try to reduce the disturbance by shifting to the left hand side. If it shifts to the left hand side, then more A will be formed, and so C and D will be used up. Now example number 3, add more D. Then the equilibrium will try to reduce the disturbance by lowering D, so again shifting to the left hand side reduces the amount of D, and so A plus B will increase in amount. And then finally, if we remove C, then equilibrium will try to increase C again, so A plus B will react. They will make more C, and so the equilibrium will shift to the right hand side. Now when you're describing these scenarios, what's important is you say what will happen in terms of which side the equilibrium will shift, and then talk about the fact that it's opposing the change. So back to add more A again. The A will be reduced, so always talk about what's going to happen and then state which side it's going to shift, or talk about yield, so C plus D is being formed in a greater amount, therefore shifting to the right hand side. So always have a couple of points in there. Now we consider the changing temperature to a situation. Now what's really important here is to highlight the enthalpy change for the chemical reaction. So this is a minus sign, so this is exothermic. So here's the scenario. 2 moles of sulfur dioxide react with 1 mole of oxygen, making 2 moles of sulfur trioxide. These are all in the gaseous state. The dynamic equilibrium has been reached. Then we change the temperature of the system. we decrease the temperature from 30 to 20 degrees. The question is, what happens to the equilibrium? What happens to the position? Does it shift left or right? What happens to the yield of product, yield of reactant? Why does it do this? So, if we decrease the temperature, the first thing we need to think about is that the equilibrium will try to increase the temperature again. It will try to oppose the change by increasing the temperature. How will it do this? It will do this by carrying out the exothermic reaction. Now, the exothermic reaction is the forward reaction. We can see that by this sign here. The value given in this the enthalpy change is always the forward reaction. So the backward reaction here is going to be positive 197. It's not written, but the backward reaction is positive 197. So the forward reaction is exothermic. The exothermic releases heat to the surroundings. And so if we decrease the temperature of that system, the forward reaction will release heat, and therefore the equilibrium will shift to the right hand side to increase the yield of SO3. So SO3 increases. What if we were to increase the temperature of the system? So this is a separate example. So the equilibrium will try to decrease the temperature again. Now it will do this by carrying out the endothermic reaction, because endothermic reactions will lower the temperature, so the backward reaction takes place. So the backward reaction absorbs heat because it's endothermic, and so the yield of SO2 and O2 will increase because the backward reaction is taking place. So shifts left hand side, and so increasing SO2 and O2. So the important factor there was to look at the enthalpy change there, plus 197 kilojoules per mole. The last part of this clip is to think about pressure. What happens if we change the pressure on a system? Well, what's really important here is we look at the number of moles on the left and the right, and count them out, write them out when you do this. So there are 2 plus 1, so there's 3 moles on the left hand side, and there are 2 moles on the right hand side. Now think about this model that if you have a situation, just a box, and you've got some particles in this box, you've got to think about how can we increase the pressure on the insides of this box? Well, we can add more particles. So adding more particles will increase the pressure of the box because the particles are bashing against the sides. How could we decrease the pressure in the box on the inside of the box? Well, we can decrease the number of particles. So the fewer the particles, the less pressure there is on the box. So back to the scenario here. Again, dynamic equilibrium has been reached, and then the pressure is increased from 100 to 200 kilopascals. So it's 1 atmosphere to 2 atmospheres. What will happen? Well, the first thing that equilibrium will try to do, will try to decrease the pressure again. It will decrease the pressure. Now, how will it do that? It will do this by favouring the reaction which has lowest number of moles, because the lowest number of moles means least pressure. Lowest number of moles means least pressure in the container, and so it will shift to the right hand side because there are 3 moles left and 2 moles right, and so the yield of the SO3 will go up. In the last situation then, we've got an equilibrium has been reached, the pressure is decreased from 200 to 100 kilopascals. What happens to the equilibrium? Well, the equilibrium will try to oppose this change. It will try to increase the pressure again. Now it will do this by going to the side with the greatest number of moles, because if we have more moles, we'll have the greater pressure again. So we'll go to this. So it will go to this side to increase the pressure. So shift to the right hand side. Shift to the left hand side, where we have a greater number of moles. So the SO2 and O2 yield go up.